Okay, let us go for the next problem. Is example 4. Estimate the size of a square footing for a column carrying axial load of 1500 kilonewton in a sand deposit having average corrected SPT value n equal to 15. Given the allowable settlement is 25 mm, gamma of the soil is 18 kilonewton per meter cube, and depth of foundation is 2 meter, and the groundwater table is at the foundation level. That means DF and TW both are equal to 2 meter. So now let us solve this. For that, we have listed the given data. Now we need to find out the size of the footing based on both allowable settlement and also based on the shear failure criterion, and therefore we will need to find out the value of phi. And I think you remember we have these correlations for finding phi value from the SPT value n. One equation gives me phi equal to root 20 n plus 15 in degrees, and the other equation gives phi equal to 0.3 times n plus 27. Now using both these equations, for n equal to 15 we get a phi approximately equal to 32 degree. Okay. Next, let us go for finding B based on our allowable settlement, and for this purpose we will first find out what is the approximate QA for the given value of n based on Peck, Hanson and Thornburn's empirical curves. So let me show you those curves. Hope you remember. These are the curves we had already discussed, and it gives us the net allowable pressure on the foundation for a settlement of 25 mm with a factor of safety of 2. Okay, and for a least width of the foundation, which will be economic for us, we can assume d by b equal to 1, and then I will get for the n value of 15, the approximate value of Q is about 150 kilonewton per meter square or kilopascal. Okay, so using that we can get, so Q for dF by B equal to 1 and n equal to 15 from Peck etc. and all. We get QNA, actually net allowable pressure, is equal to approximately 150 kilopascal. Now we also have the Tank's equation. The Tank's equation give me Q allowable as, I think you remember, it's 34.6 into n minus 3 whole thing multiplied by, I'm sorry, B plus 0.3 divided by twice B whole square. Now using Q allowable equal to 150, we can solve for B for the given value of N, and in that case I get 150 equal to 34.6 into 15 minus 3 is 12 into this factor. B plus 0.3 by twice B whole square. And when I solve for B, this gives me B nearly equal to 3 meter. Alright. Now let us see, by using B equal to 3 meter, what is the actual QA. It need not be same. Alright. Therefore, now using B equal to, this is my trial 1. I need to go for trial and error method until I get same value of QA, because it is based on empirical curve. Then trial 2, now this B, before going to trial 2, let us understand that for this B with a load of 1500, if I assume a square footing, what is the Q? Okay, let us find out that. So Q is equal to, with a B of 3 meter, I have 1500 divided by 3 square, right? And this gives me how much? This gives me is 166.66. 166.66. So this value is greater than what we have got earlier. Okay, 150 kilopascal. So our foundation will not be safe. For Q and A, for B equal to 3, for 3 meter wide square footing, as per Tank's correction, we'll get equal to 34.6 into 12 and minus 3, that means into, this is my 3.3 by 6 whole square, and this gives me nearly 125.6 kilopascal. So nearly 125. All right. Now if I use an net allowable pressure of 125, then what will be the size of the footing? So size of the footing will be B will be equal to how much? 1500 by 125. That will give me square of B, so this will be square root of this, and this gives me how much? 0.46 meter. 3.46 meter, or nearly equal to 3.5 meter. Okay, so this is my second trial. Now for the third trial, we'll see, using B equal to 3.5, what is the net allowable pressure. So QNA for B equal to 3.5 is equal to, again, 34.6 into 12 into, this will be my 3.5 plus 0.3, so 3.8 divided by 3.5 into 2, that is 7 whole square, and this becomes equal to this is equal to 122. Kilopascal. All right, so now I repeat the same procedure once again. So with this value of allowable pressure, what should be the size? Okay, and so my new B will be root over 1500 divided by 122, and this gives me how much? And this is exactly equal to 3.51 meter, which is same as 3.5, because this is also an empirical thing, and therefore my required size of the footing is 3.5 meter. All right, based on the allowable settlement. So therefore my B required is 3.5 meter. All right, so this is one result. Now I need to check whether this B gives me the bearing capacity. What is the bearing capacity for the footing with this B in the given soil? Okay, and for that I will use the phi equal to 32 degree, for which by doing the linear interpolation between local and shear failure, local and general shear failure, we have already got the values of NQ, N gamma, etc. I think you remember. NQ was 19.94 from our earlier result, and N gamma is 27.34, and therefore let us find out what is the value of Q and U. Okay, so now for phi equal to 32 degree, from the earlier problem, based on linear interpolation between local and general shear failure, we have got n Q equal to 19.94 and n gamma equal to 27.34. And by using shape factors, because it is a square footing, I need to consider the shape factors. We will neglect the depth factors for safety, and also since the load is vertical, inclination factors will be 1, and because water table is at the foundation level, so I will have to consider the water table correction factors. RWQ will be 1 and RW gamma will be 0.5 because the water table is at the foundation level, and therefore my net ultimate bearing capacity will be given by this. Okay, and so using the given values, let us find out this value. So it is, gamma was how much? Gamma was, I think, 18. Gamma is 18, yes. So 18 into the depth of foundation was 2 meter, so charge is 18 into 2 into again 18.94 into 1.2 SQ. WQ is 1 plus half of 18 into 3.5 into n gamma. N gamma is 27.34 into S gamma is 0.8 and RW gamma is 0.5. So this comes out to be is equal to 1162.692 kilopascal. So now this settlement criterion, when we started using Peck, Hanson and Thornburn curve, we know that those curves are given for a factor of safety of 2, and therefore I will use a factor of safety of 2 here also to get the QNS. So QNS will be QNU by factor of safety, and I will use factor of safety equal to 2 now. So 1162.692 divided by 2. Usually we should go for 3, but here I am using 2 itself. So 1162 divided by 2, this is 581. Kilopascal, and this value is obviously higher than 122 kilopascal. Okay, so this is greater than, I'm sorry, this is greater than 122 kilopascal, and therefore settlement governs the design. And we need a size of footing is 3.5 meter by 3.5 meter. So this is my final answer. This is my final answer. Okay. So like this, we have solved the problem number 4. So let us come to the last problem, example 5. A proposed foundation of size 1 meter by 2 meter is shown in figure 4.1. So let us see the figure 4.1. This is my figure. We have a 1 by 2 meter foundation in this soil profile. This is my sand. Two types of sands are there. Up to 2.5 meter we have 16.5 as the gamma, and for this portion, due to saturation, the same sand has a saturated density of 17.5 kilonewton per meter cube. And this is my clay layer, which is an NC clay having gamma equal to 16 kilonewton per meter cube, initial void ratio of 0.8 and Cc of 0.32. Okay, and we need to find out what is the stress intensity we can place at the foundation level so that the consolidation settlement of the clay layer is 40 mm. Okay. Find the net allowable pressure on the footing if the allowable settlement due to primary consolidation of the clay layer is 40 mm. Now let us go for the solution of this. You remember that my consolidation settlement for primary consolidation is given by H naught into Cc by 1 plus E naught into log of sigma naught dash plus change in effective stress due to foundation loading divided by initial effective stress. Now initial effective stress will be calculated at the midpoint of the clay layer. Alright, and then you remember that the average stress increase within the clay layer is the stress increase in the clay layer is different at different depths. It is maximum at the top and minimum at the bottom, and therefore the average stress increase, effective stress increase due to the foundation loading can be taken as 1/6 of increase in stress at the top plus 4 times increase in stress at the middle and increase in stress at the bottom. So when we add them, then average of that by 1/6 gives me the average change in effective stress due to foundation loading. Okay, now this change in stress can be obtained by using 2:1 method, which we have already studied. Here we have this 2:1 method. This figure you are familiar with, we have already discussed. And if I find the depth of top of the clay layer as HT from the foundation level, and depth of middle as HM, and depth of bottom as HB, then you remember that my delta at top, delta sigma at top will be, say, delta sigma dash at top will be how much? It will be Q, that is the applied stress, into my foundation size is L into B, so total load is this much, divided by the area at the top of the clay layer. And the area based on this 2:1 method, you remember, it will be L plus HT into B plus HT. Okay, this gives me the approximate increase in stress at any depth based on this. This is based on our 2:1 change in the 2:1 dispersion of the stress. Okay, similarly I will have delta sigma at mid, delta sigma dash at middle portion will be, this HT will be replaced by HM obviously, so it will be Q times L into B divided by L plus HM into B plus HM, because this is the area of the stressed portion of the soil at middle depth. And similarly delta sigma bottom will be just Q into L times B divided by L plus H of the bottom, HB, into B plus HB. And then using these values in this equation 2 above, we can find out this sigma average in terms of Q now by putting these values of, this and this here. We can get the equation, and that equation you have already seen, which is this equation. Okay, so it will be in terms of Q. Now I can put this value in the primary consolidation settlement, that is in this equation. This value I can put and then solve for Q, because all other things are known to me. SC is known, which is the allowable settlement, H naught is known, original thickness, CC, E naught, etc. everything is given. So our first job is to find out then the effective stress before construction, sigma naught dash at the center of the footing, at the center of the clay layer, I am sorry. So let us find out that effective stress. So what is my sigma naught dash from the given profile? Let me change the color. Okay, everything should not be in red. From given soil profile, I'm sorry, given soil profile, I'll get sigma naught dash as effective stress. So let us see into the figure. Effective stress before construction is 2.5 times 2.5 meter into 16.5 for the layer above the groundwater table, right? So 2.5 into 16.5, am I correct? 16.5, yes. 2.5 into 16.5 plus I need to use the submerged density. Submerged density is gamma W minus gamma saturated minus gamma W. So for this 0.5 meter it will be 17.5 minus 10, so 7.5. okay, so 7.5, that means 0.5 meter into 7.5 plus submerged density of the clay layer. Submerged density of the clay layer will be 16 minus 10, that is 6. So 6, and depth will be 2.5 by 2 at the center, so it is 1.25 into 16 minus 10, that is 6. So this is my sigma naught dash before construction, and this we can get as 0.25 into 6. This is 52.5 kilopascal. 52.5 kilopascal. Okay. And now what is HT, HM and HB? Let us find that. Now for our problem, let me write down the values of HT. HT is 1.5 plus 0.5, so 2 meter. HM is this 2 meter plus 1.25, so 3.25, and HB is my 2 plus 2.5, which is 4.5 meter. Okay, so using this, let us find out delta T dash in terms of Q. Or let me use this formula in terms of QLB. That means this formula let me use, then we'll get sigma naught dash average as delta sigma dash average will be equal to Q into L into B. L into B is, what is L? L is 2 meter, B is 1 meter. So Q into 2 into 1 LB by 6 times I have 1 upon B plus HT. So B plus HT is 1 plus 2 into L plus HT. L plus HT is 2 plus 2 plus 4 times HM. HM is 3.25, so 1 plus 3.25 into 2 plus 3.25. all right, plus sigma dash B. Sigma dash B is 1 upon, I have already taken QL common, so this is L plus HB. So L plus HB is 2 plus 4.5. Let me write down the final value, 6.5 into B plus HB. B is 1, so it is 5.5. And simplifying this, I will get the value in terms of Q, and this value, let me calculate. So this view will be okay. So after putting these values, we have got Q into this 2 by 6 is 1/3 into the value of the quantities inside square bracket comes out to be 0.2906, and therefore ultimately I get 0.0967 Q. That is my sigma dash average. Now we will put these values, sigma average and sigma naught, in the primary consolidation equation. And since everything is known except Q, I can solve it for Q. So let us do that. So now my HC, my allowable settlement is 40 mm. Let me convert it into meter. So 40 into 10 to the power minus 3, because everything is in kilopascal, so I must convert it to meter, is equal to H naught. H naught is 2.5 meter, original thickness of the clay layer. H naught is 2.5 into CC. CC is given as how much? CC is given as 0.32 divided by 1 plus E naught. E naught is, I think, 0.82 it was. Let me check. E naught is 0.8. E naught is 0.8 into log of sigma naught dashed. Sigma naught dashed was 52.5 plus del sigma dash average is 0.0967 Q divided by 52.5. Alright, and now I need to solve this for Q, and by solving for Q I can get, and from here I can find Q as 125.03 kPa. So in that soil profile, in order to have settlement of the footing as 40 mm, I can apply a Q of 125 kilopascal. Okay, so foundation load that I can put here is so result is Q net allowable, considering the consolidation settlement, is 125 kilopascal. You see, for this kind of analysis we need to have the foundation size, and while finding the bearing capacity we do not know yet the bearing capacity. So what we have to do is, based on the structure, we need to assume certain feasible size, probable size of foundation, and based on that we should do this kind of calculation to find out what is the net allowable pressure considering the consolidation settlement. Okay, so this is my result finally for this problem. So with this we stop here the problem solution part. Hope you enjoyed it, and I will upload this video as well as all these annotated files as PDF files in your Google Classroom. Thank you.